Hi, everyone, and welcome to Backer Breaks It Down. In this episode, we continue to look at vertical stretches and compressions. Okay, so we want to be able to identify the effect on a graph. We also want to be able to describe, write a formula, and interpret a function that has been vertically stretched or compressed. Okay, so what we discovered in our last episode was that a vertical size change will be indicated to us via multiplication. So out in front of your function, if you're multiplying by some number, that number indicates a vertical size change. Now the negative, if there's a negative there, remember that negative would be a reflection about the x-axis, okay? And has nothing to do with a size change. That's why it says that we want to look at the absolute value of A to determine whether it's a stretch or a compression. Because it'll be a stretch if the absolute value of A is greater than 1, and it'll be a compression if the absolute value of A is in between 0 and 1. Now, no matter whether it's a stretch or a compression, when it comes to our coordinates, we're simply multiplying the y-coordinates by that stretch or compression factor. And remember, order is important. We want to start with any reflections over the y-axis, followed by any shifts right or left, then our size changes, then reflections over the x-axis, and lastly, any shifts up or down. Right, so let's take a look at some more examples with vertical size changes. So in problem 3, it says the function g of x is obtained by f of x by a single transformation. So this first table is f of x, the second table is g of x. Right, we want to use the tables to find a formula for g of x in terms of f of x. So what do you notice? What's changed? So the y values have changed. The x values haven't changed at all. So if we take a look at a specific scenario, x is 4, f of x is 6. Over here, x is 4, g of x is 18. What caused that to happen? Okay, and so if I were to go 6 times 3, that's how I'd get 18. So notice that if I can test it out on another one, like 12 times 3 is 36, and negative 4 times 3 is negative 12. Okay, so I multiply my y values by 3. And so what this is a vertical stretch by a factor of 3. And so I can say that g of x is equal to 3 times f of x. And that shows that vertical stretch by a factor of 3. Okay, in problem number 4, it says the graph of h of x is found by vertically stretching the graph of f of x by a factor of 7, reflecting it about the x-axis, and then vertically shifting it down 3 units. Find a formula for h of x in terms of f of x. Okay, so let's take this apart piece by piece. Starting with, they said it was vertically stretched by a factor of 7. So that means I'm going to have a 7 out in front of my function, right? Here's my function f of, well, we're going to see, right? But 7 times the function will show that vertical stretch by a factor of 7. And then it said that it was reflected over the x-axis. And so I know that that's shown with a negative out in front of the function. And then it says that it was vertically shifted down 3 units. So after my function, I would have minus 3 showing that. So really there's just an x inside here because I don't have any horizontal translations. So we have h of x is equal to negative 7 times f of x minus 3. A graph of f of x contains the point 3, negative 2. What corresponding point must be on the graph of g of x equals 3 times f of x minus 8? So let's interpret and describe this, okay? So I know that that 3, right, because I have multiplication. And according to my table down here, right, this is indicating a vertical stretch by a factor of 3. And so the table also says that x won't change when I do this, but my y coordinate, I'm going to multiply by that a value. So that means I'm going to go 3 times my y value to show that vertical stretch, okay? And then I have x minus 8. So this is inside of the function, which means it's going right 8 units. And then according to my table, what changes is the x will increase by that h value. So all my x's will increase by 8. So now I just want to apply these rules to the given point, okay? So let me write down my given point, right? So we know in this problem that x will increase by 8, okay? So let's do that. X is going to increase by 8. So therefore, my new x coordinate will be 11. And then y, I'm going to multiply my y value by 3. So negative 2 times 3 is negative 6. So 11, negative 6 is on the graph of g of x. Now, domain and range problems are handled in a very similar manner, okay? So I do want to describe the transformation here. So I've got like this 3 out in front, and so I know that's a vertical stretch by a factor of 3. And I know what that means. It means I'm going to go 3 times all of my y values. The negative inside of my function, when it's on the inside, that's a reflection over the y-axis. And according to my table, that means the x values I'm going to multiply by negative 1. Okay, so I'm going to go negative 1 times x for that. And then I have plus 4. And I know that that plus 4 means it's been moved up 4. And when I move a graph up, my y values will increase by that amount. Okay, so now I want to put all of this together and find the domain and range of my transformed function. So right now I know the domain is 0 is less than or equal to x is less than or equal to 12. I know to my x values, I need to multiply them by negative 1. Okay, so I need to multiply both of those values by negative 1. So that will switch the order up, right? Because 0 times negative 1 is 0. 12 times negative 1 is negative 12. So I need the order to make sense. So I'm going to write for my domain, because I want to go from smallest to largest. So negative 12 is less than or equal to x is less than or equal to 0. Now for my range, those are my y values. I need to do 2 things, okay? I need to go 3 times the y value, and then I need to add 4, okay? So I'm going to take negative 4, right? And I'm going to multiply it by 3, and then I'm going to add 4. So let me like maybe find some more space here. Okay. So, sorry. Negative 4 to 2. I'm going to write it here, okay? So that's the original range. And I'm going to do 2 things. Like I said, I'm going to multiply each of those values by 3, and I'm going to add 4 to them. So I'm going to take negative 4 times, sorry. I'm going to take negative 4 times 3. That's negative 12. And then I'm going to add 4 to that. And that gives me negative 8. Okay. And then I'm going to do the same thing with the 2. I'm going to times it by 3 to show that stretch. And then I'm going to plus 4. And so for my range, I get negative 8 is less than or equal to h of x is less than or equal to 10. Okay. So let's actually move on to a different kind of problem. How about, okay, one of these, right? So the best way of tackling such a problem is to describe the transformation first, okay? And then write the equation. So we have our blue graph is the original function and the red graph is the transform function. So I'm seeing a vertical stretch. The question is, what is the stretch factor? Okay, that's the question. So let's like investigate. All right, so they're showing this like key point here. Okay, so like when we start at 0 and we go over to the right 2, we went up 2. Okay, and so if we look at the same kind of movement here, if I were to start at my vertex point and now we're going to go over 2, all right, notice this time I'm going up 4. So I was going over 2, up 2. Now I'm going over 2, up 4. And so that would suggest that we have a stretch factor of 2. Okay. And then I also notice a shift because the vertex was at 0, 0, and now it's here at 5, negative 2. So it shifted to the right 5 units, and it went down 2 units. So if I put all this together, I can say that g of x is equal to, a vertical stretch would come first, so 2, and then times the function. Right 5, I'm going to have that inside, and x minus 5 would show right 5, and then lastly down 2. Okay, so let's take a look at another one. We're starting with our blue function, we're going to our red function. So what are some things that you notice? Yes, clearly this thing has been stretched out. The question is, what is the stretch factor? Okay, so if we look at our blue graph originally had a height of 4. Okay, and our new graph has a height of 12. Okay, so if it went from a height of 4 to a height of 12, what's the stretch factor? Yeah, the stretch factor would be 3. Okay, so that's like, in the previous graph, we couldn't really do that because it kept going on forever. So it really didn't have like a definite height. But here, because it like stops, it's easier to see, I think, that vertical stretch. So what other things do you see? Yeah, this graph has definitely been reflected over the x-axis. Okay. And then, yes, it's also been translated. Okay. So if you want to, like this point here, like when I vertically stretch it, when I reflect it, it's going to stay there, okay? But when I translate it, it goes here. So that means it would have to go to the right 8 units. And it would have to move up 10 units. Okay. Now, if that isn't obvious to you, that's like the translation, what you could do is you could graph what this looks like after like the vertical stretch. Granted, like there's not a lot going on, but it like looks like this with after the stretch and the reflection, and then like that would probably give you better guidance or help you to see that it went right 8 up 10. So if we put all together, we're going to say the function g of x is equal to show the stretch, we're going to have 3 times the function. The reflection over the x-axis, I would have that negative out in front as well. Right 8 is x minus 8, and up 10 is plus 10. So there you have it, vertical stretches and compression. Basically, we're looking for multiplication in the very front of the function, and that will tell us that there's been a vertical size change. It's a stretch if that absolute value is greater than 1. It's a compression otherwise. Okay, and what that means is all the y values are going to increase by a factor. So we're going to multiply all our y values by that stretch factor or compression factor. And that's how Backer breaks it down.